Okay.
Let's kick it off. So thank you all for
Okay.
coming. I'm absolutely excited about to hear from Peter Behroozi. The name Behroozi to me is synonymous with how to fill in, to match dark matters with halos with galaxies. So that's where I have a lot to see my students mention his name a lot. So I'm absolutely excited to hear this talk. He's your, what did you say, scientific cousin? That's how you introduced him?
Academic,
Okay.
well,
Academic
well,
cousin, there we go.
we
But
share a grant advisor, Joe Primack. But yeah, of course, Peter is also known for developing Rockstar and Consistent Tree, and of course, the latest and greatest Universe Machine. And Peter will tell us all about it today. Did I miss anything,
please
Peter?
take them.
Thanks, Aaron and Benny. So I'm happy to be here. So the level of this talk, or the goal of this talk, is to talk about how empirical models might influence HWO and the science and policy decisions surrounding this observatory. And so the level of this talk is more geared toward the experts in the working group. And so if you have questions about something I bring up, please stop me and ask about them, because I'm happy to explain. I just didn't include as much introductory material as I normally would, hoping that people would ask questions about the things that they were interested in. Okay. So the title of my talk is about using empirical models to explore science uncertainties for new instruments, observatories like HWO. But there's also a broader point that I wanted to mention about policy, which is, if we look at cosmology, it's sort of embedded in the DNA of every new cosmologist now that whenever you combine data from different probes, from different surveys, then you get much tighter constraints on what you're interested in, that is the physics of the expanding universe. In our case, in galaxy formation, we've sort of yet to absorb this as tightly. And so while in cosmology, it's very, very common for new results to combine many, many different probes, it's somewhat less common for papers in galaxy formation to try to combine many different probes together. And I think that's not the fault of individual scientists. It's sort of what sort of ecosystem have we developed and discussed in our field for how we think about how to do galaxy formation science. And so there's sort of two broad points here that I want to mention. So I think the impact from an observatory like HWO will be much, much higher when there's a focus on reusability and combinability of the data. And so that means thinking about things like selection effects and biases. How are the data gathered? How are the data made available so that other people can reuse it, on one hand? And on the other, also thinking about how can we establish an environment, including funding, including support for theory and machine learning work to combine different data sets. And so this is sort of embedded in a field like cosmology, where you spend a lot of time learning about different instruments, learning about different probes, whereas there's somewhat less focus on that in galaxy formation. And I wish there were more focus on that in galaxy formation, because I think the science that we could achieve would be much more impressive as a result. Okay, so let's see a little bit about how this works. And the example that I'll give of how this works is empirical models. So I'll give you a bit of an introduction for empirical models for galaxy formation, as well as for supermassive black hole formation, and then talk a little bit more again about the impact of exploring science uncertainties for HWO. Okay. So with empirical models, the basic idea is that the actual growth of galaxies and SMBHs must be consistent with all available observations. And for those needing a little bit more of an introduction to empirical models, you already know and love one from cosmology, because we talk about a dark energy density and a dark matter density, but we have no idea what these two things actually are. And so instead, what we have is an empirical model that says there's some amount of dark matter density with an equation of state, there's some amount of dark energy density with a different equation of state, and these two things combined give us the expansion history of the universe that we can measure. In galaxy formation, it's a little bit more ambiguous, because we don't have sort of a standard empirical model for how the galaxies form or black holes. But the main point is that is the same. The actual growth of galaxies and supermassive black holes must be consistent with all available observations. And because we have millions and soon billions of observations of galaxies and supermassive black holes, there is a lot of constraining power from our observations to fix how must galaxies and supermassive black holes evolve. And it's useful to consider combining all this information because of how hard it is to watch a single galaxy or a single supermassive black hole evolve, right? Because human lifetimes of, say, tens or 100 years are much, much shorter than the characteristic timescales on which galaxies and supermassive black holes evolve. And so it actually then becomes useful to think about how to combine all this information from galaxies and black holes observed at different ages of the universe to understand how they grew. Okay. So the classic example of this is recovering the relationship between galaxies and dark matter halos. So in Lambda CDM, we think that galaxies grow at the centers of dark matter halos, and there's some relationship between the stellar mass of the galaxy that forms, that's M star, the host halo mass, and the redshift. And this is important for galaxy formation physics because we think that this relationship encodes something about the physical processes shaping the galaxy. So just to give an example of this at redshift 0, if you look as a function of the host halo mass of the galaxy with sort of scales labeled here, dwarfs to clusters, and you look at the ratio of the stellar mass to the halo mass, that's proportional to the fraction of baryons in the halo that have turned into stars. And you see this characteristic shape where you have a peak in the formation efficiency around the mass of the Milky Way, and different slopes on either side, which tell you that different types of physics are responsible for shaping galaxies in low mass halos and high mass halos. We think, of course, those are supernova or stellar winds and AGN feedback for the massive halos. Empirical modeling can give us, though, this relationship at any redshift that we like. At redshift 0, there are lots of different ways of measuring or inferring halo masses, from X-ray measurements of clusters at the massive end, weak lensing, clustering, satellite kinematics. And so at redshift 0, there's a really large variety of observational ways to get at this relationship between galaxies and halos. At higher redshifts, it's a lot harder to do any of those observations, but it turns out that there's a very simple empirical way of getting at the galaxy mass halo mass relationship. And that is by combining data from observations with data from Lambda CDM simulations that tell us how many halos there are at a given halo mass. Okay, so let's briefly go over how this works. So at redshift 0, we can't always directly measure the halo masses, so what can we do instead? We can do a form of guess and check. And so the idea here is that at, say, for example, redshift 1, we might guess a ratio of stellar mass to halo mass, that is the galaxy formation efficiency as a function of halo mass, and then we can compute how the universe would appear under that guess. So what I'm talking about here is exactly a form of forward modeling where we have an underlying assumption or a guess about how the universe works, and then we want to compare that guess with observations to see how closely it matches different observations that we can take. And so just as an example here, if I say the ratio of stellar mass to halo mass in a 10 to the 14 halo is 0.1%, I can go to a Lambda CDM simulation at redshift 1. I can calculate the number density of these halos at redshift 1. And so from that, I can calculate, so 0.1% would correspond to a 1011 solar mass galaxy. So then I can calculate the number density of 1011 solar mass galaxies, and then compare it with observations of how many, in fact, 1011 solar mass galaxies there are at redshift 1. And if my guess is wrong, which the first guess is usually wrong, I know how to fix it, because I can see my guess gave me too few galaxies at redshift 1, so I need to increase the amount of stellar mass that I assign to different halos. And so if I just flip back and forth here, you can see what effect that has in the observable space. So if I just bump up everything in this space, I move all the stellar masses to the right in this space. And now I overproduced stellar mass here, so I need to sort of lower these assigned stellar masses again. If I iterate enough times, then I can recover the observables on this panel, and then my inference on the left-hand panel is then the relationship between stellar mass and halo mass. And so all that I had to do is make the connection that the observed distribution of stellar masses and then the simulated distribution of halo masses were enough information to combine to get me at what is the efficiency of star formation in galaxies. The only assumption that I'm using in this process is that there is a tight connection between stellar mass and halo mass, which we know at redshift 0 to be about 0.2 dex scatter in stellar mass of fixed halo mass across many decades of halo mass. Okay. I can repeat this process at any redshift, of course, not just redshift 1. I can repeat this process anytime when we have observations of galaxies. And so I can combine measurements from Sloan Digital Sky Survey, from Primus, from Hubble's and the CANDLES fields to get at an enormous range of ages of galaxies in the universe and reconstruct over that entire time, then how did the galaxy formation efficiency look not only at redshift 0, but at all previous redshifts where we have information about galaxy masses. Okay, so I'm just going to pause there and ask if there are any questions from folks so that I can fill in the details of everything that I skipped.
Well, there's a question from Hannah. Go ahead.
Yeah. So I understand you have data points on the plot on the right, but you kind of seem to have data point like things on the left as well. Yes. So what's that?
Yeah, great. So what I'm doing on the left is I have a parametric form for the galaxy formation efficiency, which is informed by all the measurements at redshift 0 where we have the tightest data. So I make a parametric form which is flexible enough to match things at redshift 0.1. And then I constrain that and its evolution according to the galaxy number densities on the right. And these error bars are really the width of the posterior distribution. So they shouldn't be thought of as individual data points on the left hand here, but instead they're sort of the range of typical uncertainties like the 1 sigma distribution around this median line here. So each of the different colors corresponds to the different redshifts.
Okay, and the MCMC here just means you use that for the likelihood computation.
Yeah, so I should have said the fancy name for guess and check is MCMC.
Thank you.
Great. Okay. So then if I take this a step further, I've mentioned here sort of the basic way in which we recover the relationship between galaxy mass and halo mass. We can also do things like ask, what are the formation histories of galaxies? And so the way that this works is, again, by tying together two different data sets. So what I did previously was I said, okay, I'm going to add in information about dark matter halo number densities to galaxy number densities. And now I can recover the galaxy formation efficiencies as a function of time. Now, if I add in growth trajectories for dark matter halos from simulations, now I can recover even more about how galaxies actually formed over time. Okay, so how does this work? I can look in a simulation and I can say for halos in a given bit of mass at redshift 0, I can trace their progenitors to earlier and earlier times and recover the range of progenitor histories of a given bin of halo mass at redshift 0. That means I can take halos at redshift 0, I can go back to my relationship between galaxy mass and halo mass, and I can figure out, okay, yeah, in 10 to the 12 solar mass halos, I have Milky Way mass galaxies at redshift 0. Then I can trace those halos back in the simulation to see what their typical masses were at, say, redshift 1 to 2. And then I can ask, okay, what were the typical galaxy masses in those halos at redshift 1 to 2? And I might find that they are maybe a factor of 7 smaller at that time. And so then what I can do is I can say, okay, at any redshift in between, I can go back to the stellar mass halo mass relationship and recover what was the average trajectory of galaxy growth across time for this population. And so that's nice because I can reconstruct a movie, as it were, of how real galaxies observe with no assumptions about the subgrid physics that went into forming those galaxies, right? So for a hydro simulation, I can watch how galaxies observe, but I'm always wondering the assumptions for feedback that I put in make sense. But here I can just ask the universe, how do galaxies grow over time? And with enough information, with enough galaxies observed at different redshifts and enough information from gravitational simulations of dark matter, I can actually then recover how real galaxies grow over time. And so here's an actual then movie created by Casey Popovich. And so what you should take out of this is not necessarily that the features of the galaxies are right in this movie, but the stellar mass is right in this movie over time. And so we can say for a galaxy at redshift 0 that looked like the Milky Way, its typical stellar mass corresponded to that of these postage stamps as you go back earlier and earlier in the history of the universe. I won't say much about the sort of the future of empirical models, but I will say a sentence here that over time, empirical models are growing to incorporate more and more observables about galaxies. So semi-lake models are much farther ahead in this sense of having things like chemical abundances, morphologies, gas fractions, and so on. Empirical models are now starting to catch up. So in the future, we will be able to link galaxies by more than just stellar mass and star formation rates, but we'll be able to say, what is the evolution of the size of the galaxy or its gas fraction and things like that. Okay. I want to talk a little bit about the most recent progress in empirical models, including modeling black holes. So I mentioned that we can model the relationship between galaxies and halos, but we can also try to understand the relationship between black holes and galaxies. And so just as I recovered the evolution of galaxies by combining information about the evolution of dark matter halos with observations of galaxies, I can leverage the galaxy formation histories that I now know to recover something about the formation histories of supermassive black holes. And so just as before with galaxies, we can measure the relationship between, just as before with the relationship between galaxies and halos, which we could measure at redshift 0, we can also measure the relationship between supermassive black holes and galaxies at redshift 0. But at higher redshifts, it's much, much harder. And the reason it's much, much harder is we can typically only see the brightest growing black holes, say the 1% most active black holes at higher redshifts, whereas then the remaining 99% of the population is unobservable. And that means there's a potentially huge selection bias in measuring the supermassive black hole galaxy relationship at higher redshifts, because we just don't know what the rest of the population is doing compared to the population that we observe. Okay. But it turns out by combining existing data sources appropriately, we can nonetheless reconstruct how real supermassive black holes in the universe actually evolved, again, without making any assumptions about the physics of accretion onto black holes. Okay, and so this is how this works. I mentioned previously how we could reconstruct the growth of galaxies from the observations of number densities of galaxies, as well as growth histories of dark matter halos. If I start with the evolutionary history of galaxies, so if I have a, say, bin of halos at redshift 0, and I can measure their galaxy masses inside, and then I can trace those halos back to an earlier time and measure again the galaxy masses inside, I can use information like this to reconstruct the growth histories of supermassive black holes. Okay, how does this work? At redshift 0, I know the mass of the galaxy inside the given halo bin, and I can go to the black hole mass bulge mass relation to say, what was the typical black hole mass in these galaxies at redshift 0? Okay, at higher redshifts, I don't have this. I don't have any relation like this that I can draw on. But at higher redshifts, we do have growth rates for supermassive black holes from X-ray observations. So the paper I picked here is from James Aird, but there are many other examples of measuring black hole growth rates as a function of galaxy mass at earlier redshifts. And so even though I don't have a mass, I do have a growth rate, so I can tell how fast that supermassive black hole is growing over time. And so what I can do is I can go at every redshift between redshift 0 and the highest redshifts to which I can measure growth rates, and I can measure the growth rate over that time. And I can say, well, when did the mass in the black holes at redshift 0 assemble over this time period? And from that, I can reconstruct the growth history of the supermassive black holes in these galaxies at redshift 0. So this is not the individual black hole growth history, it's the ensemble averaged black hole growth history from combining all the growth rates of the black holes in this population. For those who are familiar with the Sultan argument, you can think of this as a bin-Sultan argument. So whereas the Sultan argument is relating the cosmic supermassive black hole density to the cosmic quasar luminosity density, instead, what this is doing is it's selecting a subpopulation of galaxies in the universe, adding up all the black hole mass in that subpopulation and adding up all the quasar luminosity or black hole X-ray emission in that subpopulation over time. Okay, so regardless of which way you think about it, we can use this information to then reconstruct growth rates of black holes over time in the real universe. Okay, so this is really interesting because if we look at any black holes individually, we can never say, yeah, this black hole grew this way over time, because everything about that growth history is sort of hidden behind the event horizon. But with a technique like this, we can combine observations across many different redshifts and then reconstruct what was the evolution in black hole growth over time. Okay, so let me say a couple more words about how this works. I mentioned where the information comes from. What do we do in practice? We start with the dark matter simulation, and then we put in a minimal model for the galaxies and black holes. So this is a fitting function, nothing related to sort of a subgrid physics model, but you could imagine power laws or splines stitched together for a star formation rate as a function of halo properties and redshift. Also a distribution of black hole growth rates that's a function of galaxy mass and redshift. This model is applied to dark matter simulation, and then you have sort of galaxies and black holes embedded in every mass bin and redshift bin in the simulation. From this, you can calculate how the universe would appear. So you can sort of reconstruct a mock universe for any given guess about how do galaxies and black holes grow in dark matter halos. And then you can compare that with the real universe, again, use MCMCs to then constrain in this underlying space of interest, how do black holes and galaxies grow? And this is a process that took about 6 years, 7 years from start to finish, because it involved combining a huge number of different data sets. So it involved combining all these galaxy data sets, things like stellar mass functions, star formation rates, cosmic star formation rates, quench fractions, UV luminosity functions, with statistics from n-body simulations like mass functions and merger rates of dark matter halos, with a ton of different information about black holes. So things like the black hole mass, galaxy mass relationship, things like the X-ray occupation fractions of galaxies. This is the distribution of how bright things are as a function of stellar mass and redshift, with quasar luminosity functions, with active supermassive black hole mass functions. So there's a crazy amount of different data sets, each with their own problems and systematics and uncertainties that all have to be dealt with to be able to combine themselves consistently into a single package. Okay. But there are a lot of cool results that come out from doing work like this, which are sort of beyond the capability of any single instrument to be able to do. And so one example of that is, for example, recovering what is the relationship between supermassive black holes and galaxies, and how does that change over time? And the answer is that there's not a big change in the black hole mass galaxy relationship over time that we infer. And that's connected to observations that the typical sort of relative black hole mass growth rates in galaxies are similar to the relative growth rates of galaxies themselves across mass and redshift bins. The other cool thing that comes out is an ability to interpret observations from different instruments self-consistently. So as an example of this, we see at high redshifts especially that most instruments are able to only get the brightest and fastest growing black holes. But we know that these are a subset of the overall population, and that typical black holes are often growing at much lower rates than are observable with most instruments. But then from time to time, we get a new instrument like James Webb, which is able to probe down to the luminosities of these more typical objects. And so what we find is strong evidence in the observations for Lauer bias. That is, the brighter black holes tend to be more offset from the black hole mass stellar mass relation. And that when you compare James Webb measurements with previous observations of quasars, you tend to see large offsets between the estimated black hole mass, or the offset between the black hole mass and the black hole mass galaxy mass relationship, compared to the more to the brighter quasars. Okay, so let me stop there and ask again for questions. Yeah, so there are a bunch of questions.
I'll let Daniel go first.
Thank you. I can also wait, but yeah. So I was just wondering if you are using the observed black hole masses at higher redshifts to constrain the model, or just the sort of anchor at redshift 0 plus the sort of accretion rates, and then whether, I guess, from observations at different redshifts, as you are saying, many observational results sort of point or try to argue that there is a systematic, like, large offset with higher normalization at higher redshifts. And I guess going back to the question of, does your model basically predict very weak evolution, and maybe the biases can explain most of what we see in terms of
We do use measured black hole masses at higher redshifts, and we take into account the fact that there should be some bias between the luminosity and the mass of the black hole that we measure, or that's measured. There are questions about the systematics, of course, of measuring masses, especially as you go to higher redshifts and have to use things like carbon-4 or other lines that may be offset from other measurements. And so Howen has also tried without active black hole mass functions, but the conclusions are largely the same. And the reason that the conclusions are largely the same is that most of the data constraints are not coming from the active supermassive black hole mass functions, and are instead coming from the Adrian occupation fractions that's telling you the growth rates and the redshift 0 relationship.
Okay.
And so as a result of that, then most of the, I mean, these are more included as a consistency check rather than providing strong constraints on what the black holes are doing.
Great. Yeah, thank you.
Great. Yeah, Benny.
So this is, for me, is the it's outliers. So here's where you point out that outliers are sort of biased, but even in the redshift 0 stellar mass supermassive black hole, one of the things, like, yes, there's a correlation, but there's lots of scatter around it, which sort of are you averaging out over these things, right? So you're sort of averaging. Correct me if I'm wrong, but it feels like you're sort of making an average growth rate and an average history for all these things. Meanwhile, there's lots of local, small scale, small time scale fluctuations around it. So that's what the scatter sort of, this is the end product. So this is sort of the scatter around this is the end result of having lots of stochasticity happening. So if you have an outlier that's either really below or really above, can that inform your model as well? So it's not just the mean, but it's also the variance, but also the extremes. The extremes tell you something here as well.
Yes. So the typical trajectory of empirical models in terms of sophistication is get the average right, then start to get the scatter right, and then look at what the outliers are telling you. And so because the bulk of the information is also on, by definition, typical systems, then it's easiest to start with typical systems, and then you progress to more extreme ones. The focus of Trinity is to ask what is sort of the average growth history, and as well as the relationship between supermassive black holes and galaxies on average over time. Helen is now working on the next steps, which are to build a model that will get more of the individual variation, sort of which black holes are above and which black holes are below, and how does that connect with the galaxy properties and mergers and things like that. And then the focus will be on outliers, like what went wrong. And there's a lot of interesting things that happen there, as well as a lot of hard work to understand, well, how prevalent are these things really? Because the more that you get into outliers, the more that you get into selection effects, and the more that you get into really the details of how the measurement was made. So if you just take a data set and you ask what are the most extreme things in that data set, like if you go to Sloan and say, what are the most massive galaxies in Sloan? The most massive galaxies that pop out are the ones with cosmic rays or bad masking or all these like nasty things that happen. And then you get into the things where, oh yeah, there are a bunch of errors in the fitting pipeline and the stellar mass fits that drove it into some crazy corner. And then you finally find the real like extreme outliers. And so there's a lot of extra work that has to go in to understand that, which is why it's sort of at a further stage in what we're doing right now.
It's coming from the I have my favorite object, but it is weird.
Yes.
Slant, but it's the kind of thing where it's like I do have this feels like it does tell me something. So connecting this back up to here would be fantastic.
So it's worth talking about that too, because I have my favorite object and it's weird. There's a immense potential for discovery from weird objects because they exactly tell us something that's not typical about the population. If we want to combine the data from the weird objects and sort of build a better science around it, there's one aspect which is, oh yeah, this weird object is telling us that we need new physics, and so we better have a model that's flexible enough to allow for these weird objects to happen. But unless people are super, super careful about selection for weird objects, it's really, really hard to build a physical model that gets the right number of weird objects, because the selection of a human going through a data set and saying, hey, this is weird, let me get more observations on this, that's really, really hard for us to model. We can model a selection effect like, oh yeah, like we looked at all things with this color cut or beyond this magnitude or with this separation from other galaxies. Is really, really hard to model what a human thinks is interesting and not interesting. And so this gets back to the earlier point about data reusability. How do you define your selection so that a weird object is reproducible in simulations as well, or the selection for weird object is reproducible in simulations, so you know whether your simulation is matching that object or not. Great.
That was an excellent answer. Thank you.
Other folks? Okay. So then I briefly want to mention about exploring uncertainties. And so the other thing about empirical models, I didn't mention too much about the functional forms that are used. I mentioned very briefly that there's sort of fitting functions, which could be splines or power laws. Splines are usually used for interpolation, but power law is often used for extrapolation. And that's typically what I do for all of my empirical models, what Howard did for Trinity, is that we constructed power law relationships so we might be able to extrapolate a little bit beyond the data sets that we used under the assumption that the physics remain the same. And so let me see if I can talk a little bit about this. If I go way back to one of my first slides about the relationship between, say, star formation and halo mass, I mentioned earlier that a change in physics means a change in slope of this stellar mass halo mass relationship. So as we see, as we go from small galaxies to large galaxies, there's a change in slope of the stellar mass to halo mass because there's a change in the dominant feedback mechanism for galaxies. And if I go to lower and lower mass, unless there's some change in physics about what sets dominant feedback mechanism, then it's reasonable to expect a power law to continue down to lower and lower masses. And similarly to higher and higher masses, it's reasonable to expect a power law to continue if the physics is the same. And so in that sense, it's possible to extrapolate from empirical models. And the implicit assumption there is that the physics remains the same, that there's no new physics coming in your extrapolated region that bends the power law into some different direction. So based on that assumption, we made predictions for James Webb in 2020 before launch about what would the UV luminosity functions, stellar mass functions, other things, of course, also look like, as well as the range of uncertainties. And so, as I mentioned before, when you use guess and check or MCMCs, you're matching to data with errors or uncertainties. And so you can explore the range of parameterized power laws that are consistent with the range of uncertainties allowed by existing observations. And so the dark shaded regions here correspond to sort of the 1 sigma, and the light shaded regions correspond to the 2 sigma uncertainties around the extrapolations based on the assumption that sort of physics remains the same. And what we found with James Webb is that actually, yes, the observations were sort of reasonably within the error bars of our expectations. The particular reference I picked here is, of course, the spectroscopic one. And so maybe you can argue that I'm sort of cherry picking after the fact, that there may be more issues at redshift 15 if we believe all the photometric redshifts. That, of course, will get validated in time. The main point is that empirical models here give us a baseline benchmark with which to make predictions. In other words, if all physics stays the same, if things just smoothly extrapolate with power laws to unexplored spaces, then we have a way of estimating what new telescopes will see when they look at those unexplored spaces. And we also have a nice way of quantifying how we should design surveys. So in other words, we can take a mock catalog where the universe looks like this down here and compare it with the universe that looks like this. And we can ask what survey designs will best distinguish these universes and reduce the uncertainties with the smallest amount of observational time. Okay, so I just want to mention that as then the closing to the original title of how can we use empirical models as a way of combining all existing observations and ask sort of what's still possible and consistent with all the physics incorporated in the space that we see, extrapolated then to unobserved regions of parameter space. Okay, so main takeaway points. Let me now have a good time for some questions and discussion. I think the two most important lessons that I've taken out of building empirical models is one, that we really need to build an ecosystem, including funding around data reuse and synergy that will maximize the science outcome from new telescopes, new observatories, by combining their data with everything, all the millions and billions of observations that other telescopes have given us. And the last point then is just what I touched on last, which is that empirical models can help give back to this process. So not only we suck in everyone's data and try to say something about galaxy formation, but also we can give back and say, how can you best distinguish between the range of existing uncertainties with new telescopes, new designs, and new missions? Thank you.
We only have one question.
So I was wondering, like, how like HWO could improve like theory in terms of, for example, measuring black hole mass. Because if you see like the new gravity paper, they use like UV data like C4H beta to estimate black hole masses, right? But sometimes they found that there are like higher, like some very broad lines which actually traces the age in wind, and at high redshift all the black hole mass has been estimated to like the broad line region. So I was wondering if that actually introduces some kind of uncertainty to get like the actual black hole masses, which in turn creates some kind of outlier. So yeah, I'm interested to hear your opinion on this.
So generally, basically the most robust lines end up shifting into the infrared, and so you would want some kind of infrared observations to estimate more reliably black hole masses. I think the benefit of an instrument like HWO will actually be about the other side, which is about the galaxy masses, because it's often super hard to estimate the mass of the galaxy when there's a giant thing shining in the middle. And so in that sense, rather than improving the black hole mass, I think you would get a much better idea of what are the galaxies like that are driving these very, very bright black holes.
Thanks.
Looks like we
Yes,
have a
I'll
question
go.
from Anna. Go ahead.
Yeah. So you flashed through the slides with kind of like which constraints go into your current generation of models very quickly. So I'm just gonna ask specifically, and I guess we don't have that much data yet, but for future releases, are you thinking of including gaseous halos, so circumgalactic medium, intergroup medium, intercluster medium as one of the constraints? And if so, how important do you think they will be?
Yes.
Or already are?
Yes, so there's already been some work by HWO to incorporate ISM constraints. And so H1 and H2 masses and how they evolve with halo mass and redshift. CGM constraints are also really interesting, and I think that's a natural next step. So we're building right now a model for gas phase metallicity in the universe machine. And a natural constraint on the whole metal evolution cycle is the metallicity of the CGM, but you also need to know what is the mass of the CGM to be able to use that self-consistently. And so the whole progression is to build out empirical models of all aspects of galaxies, not just the sort of stellar mass, but the morphology, the surrounding gas, everything that we can measure observationally.
So I'm sorry, because you actually my internet broke at the beginning when you started talking. So I just heard that part about ISM and CGM. So what about the bigger halos, the kind of intragroup, intercluster medium? Because on that there's already a lot of data and constraints.
Yes. So I think I mentioned that we're not quite there to use CGM data at present, but we want to.
Okay.
And in the cluster scale, there's a lot of information about that because you can directly measure the CGM with X-rays.
Yeah.
And we have a question from Kenya.
Yeah, thanks, Peter, for the great talk. So I was wondering if you want to use a model like Trinity to make predictions for different cosmologies. So do you have to, I guess, run, an n-body simulation with the cosmological parameters that you want, and then sort of run the full NCMC again, sort of retuning or refitting the model in a sense, and then it's all sort of related to this. What would it mean then the redshift zero anchor, like the stellar mass halo mass relationship at redshift zero, which is sort of observed? How would that, what would we do? What can be done for different cosmologies?
Great. So there's sort of a bunch of different questions and sort of science cases that you might make. For example, you might be asking, what happens if you marginalize the constraints of a cosmology? Or you might be asking sort of, what are the predictions for how black holes would evolve differently in a different cosmology? So what would happen is that the data would all be the same. So the observational data would all be the same, modulus A corrections for how the cosmology affects the absolute magnitude of things. But then the underlying thing that would change would be the dark matter side. And so you would use a different mass function for Trinity, as well as potentially different merger rates in Trinity. And so in practice, if you had an emulator that would spit out a mass function and merger rates as a function of cosmological parameters, then you could either generate for any cosmology the results of a given Trinity model, or try to fit and marginalize over cosmology uncertainties for the, say, relationship between black holes and galaxies across all the existing data constraints.
Okay. But I guess if we go sort of the first route with sort of a new halo mass function, which corresponds to some other different cosmology, then if we just apply that to the existing Trinity, which has been built to match observations with some other cosmology, that means that the predictions for the new cosmology would not necessarily match observations. Okay, yeah.
Yeah, and so what you're doing there is taking a specific relationship between galaxies and halos and supermassive black holes and applying it to a new cosmology, which would give you different observables. Whereas if you wanted sort of the opposite, what is that relationship given the existing data and a choice for cosmology? That's sort of a different mathematical question.
Okay, yeah, great, thank you.
Okay, is there any other questions? Going one, going twice. If not, let's thank Peter again for the great talk. Thank you for doing this, Peter. Benny, do we have any announcement?
No, we have the next one is already in the works. So thank you so much. Sorry, I was already thinking about the implications. So yeah, that was a fantastic talk. Thanks. Like anything that makes me start, the brain starts fizzing is good. We'll hopefully all see you next time. We'll have this on the YouTube channel soon. And Peter, can we please have your slides so that we can put them on there as well? Because I tried to take some snaps from it, but it was not fast enough. So, that was really good. I love the spaces for questions. So we didn't interrupt you, but also we got to ask right there and then. So thank you so much.
All right.
Thanks,
Everyone.
everyone. See you in a month.
Thank you.
Bye.
See you in a month.